We'll now talk about another exciting topic that's related to classification of estuaries based on the hydrodynamics. If you remember the first lecture, we talked about classification of estuaries. So why do we come back to it now? And the reason is because there's a classification that has withstood several decades because it's based on physics, on the hydrodynamics of a system. So it's a general. Now people are realizing that. Well, we'll discuss the problems with it later on, but it has withstood several decades. You see that this was proposed in the mid-60s, and it has a very strong hydrodynamic basis, and that's why it's good. And we talk about it now because it requires a little understanding of the physics of these systems to be able to get a grasp of what this really means. And it has a lot of insight, this approach, as I hope you'll realize. So what they did, so this is the Hansen and Rattray classification of estuaries. And it's really restricted to any kind of estuaries, but they start their approach looking at partially mixed estuaries, ignoring lateral variability. So keep that in mind, that there's no lateral variability, in which case we come back to the framework that we had established way back. What does that tell you? What is that framework? Right, pressure gradient and friction, the longitudinal framework that we established, and that we saw that it can be modified in time and in space, so that maybe the advective terms should appear here, maybe the Coriolis should appear here also. And the continuity, remember there's no lateral variability, that's what there's no dV dy there. And then the salt balance is between advection and diffusion, it's given by that relationship. Remember what these coefficients represent, this K sub x and K sub c. Eddy diffusivity of salt. Any idea of the range of values that you could see in this? This is just general culture that should be in your discs.
Throw it out there.
Throw it.
10 to 100.
What? 10 to 100 what?
Units.
It could be 10 to 100 units, but depends on what units you're talking about. It could be 10 to 100 centimeters squared per second. That's what you meant?
Yeah.
That's right. It's really 10 to the minus 4 to 10 to the minus 2 or so meters squared per second. Remember? For the vertical. But for the horizontal, how about the K sub x?
It's less.
Less? What's easier for in a salt blob? What is it easier to diffuse like that, or diffuse like this, or like that? The vertical is easier to diffuse in the vertical. In the horizontal is easier in the horizontal. The horizontal gradients will cause it to spread like that. So if you release a sphere of salt, how will it elongate? It will elongate like this, right? It will expand like this, but much more like this than like that, because the rates of horizontal diffusion, although this is turbulent diffusivity, the rates of horizontal diffusivity are larger than the vertical. So these K sub x are 10 to the 1, or 10 to the 0 to 10 to the 2 at the most square meters per second for the horizontal diffusivity. So several orders of magnitude larger than the vertical. Anyway, like I said, that's general culture. What we have here is the salt balance given by advection and diffusion. And then the equation of state is given by that. What do we mean by that expression? See if you remember what we've talked about. Remember what the equation of state is?
Relationship between salinity and temperature and density.
That's right, salinity, temperature, and pressure to density. So an equation of state that looks like that, what does it tell us? Again, this is general culture. That these things appear on papers that you read. So after reading papers, they will stick in your disk.
Density change.
Right, that the density only depends on salinity, exclusively on salinity. Pressure and temperature have a negligible effect on density, and that's reasonable in shallow estuaries. And so the beta, what does the beta represent there? It's also a coefficient of what? Notice that we have a 1 here that has no units. Salinity, well, salinity should have no units either, but it reflects a concentration. So the beta should be related to the salinity, how it expands or contracts with changes. So the effects of salinity on density is given by that Hallan contraction coefficient. And remember the values for these? Remember when we talked about the thermal expansion coefficient? And we showed a contour plot of how that thermal expansion coefficient changes with temperature and salinity. This is the equivalent but for salinity, the effects of salinity on density. And this changes much less than the thermal expansion. This Hallan contraction is around 7.8 times 10 to the minus 4. So what that means is that with every 0.78 change of salinity, with one unit change of salinity will cause a 0.78 kilogram per cubic meter change in density. I'll say that again. A change of salinity of 1 would be equivalent to approximately a 0.78 kilograms per cubic meter change in density. Remember, for temperature, it is 1 degree change in temperature would represent approximately a 0.2 kilogram per cubic meter change. So typically, the salt is 4 times more effective than temperature per unit to change the density. Okay, so given that general culture review, what NASA and Radford do with this equation is they non-dimensionalize the variables, and we're not going to go through all the procedure, but they non-dimensionalize the current velocity as the river flow, that is current to the river flow, and then the salinity as a function of a long estuary and vertical distance. And for that, you get two-dimensionless parameters when they do all this non-dimensionalization of the momentum equations and salt and continuity equations. You get two non-dimensional parameters that can characterize any estuary. That's for the case of no wind stress. The first parameter is the tidal mixing parameter, and that's that ratio there, where case of Z would be, what is case of Z? You said the vertical eddy diffusivity of salt. Case of X at 0. Case of X is the horizontal diffusivity of salt at the river. B is the width of the estuary, and R is the river discharge. So this is how effective are the tides in diffusing the salt in the estuary. So this is a measure of the diffusivity of the system caused by tides. How efficient are the tides in causing salinity to be mixed along the basin? Okay, so that's from the tides. And then we have the gravitational circulation. That's based on the estuary Rayleigh number, which is given by this expression. That depends on gravity, the how would we call this, beta? Or something like that, and then the salinity, and then the depth cubed divided by the eddy viscosity, and the same parameter, the horizontal eddy diffusivity. So these non-dimensional parameter tells you how effective, instead of tides now, how effective convection or gravitational circulation is, or the estuarine circulation, how effective that is to transport the salt, or to move the salt around in the estuary. So essentially what we're looking at here with these two parameters is the relative contribution from mixing versus gravitational circulation in transporting salt. If you look at the salt balance equation that we showed before, it's advection diffusion equation. So this would look at advective processes, and this would look at diffusive processes, those parameters. Okay. So those parameters have too many other variables. They can be we can use surrogates to characterize the estuary, and those surrogates will be what we call the circulation parameter. And the circulation parameter is the ratio of the net surface current to the mean freshwater velocity through the section. So let me see if we have, yeah. So that's the ratio. What range of values do you think you can get from that? Can you imagine what we mean here? So let's again put our classroom here in the estuary. So this is the x direction. And imagine the surface flow going in that direction. The surface flow going positive, let's say. And what can we say about the sectional average speed? How do you want it to be? The average speed throughout the cross-section. Do you want it to be in the same direction as the surface? Do you want it to be in any other way? Because say, if we have an estuarine circulation, that sectional average speed will be large, small, negative. If we have surface outflow throughout a surface layer, and then near bottom inflow all across this basin, the cross-sectional average will be very small, close to zero, right? Or very small. So this ratio will be large. If the denominator gets close to zero, this ratio will grow large. Now what happens if we have that throughout this whole section, we have flow going in the same direction approximately as the surface? So this ratio will be small, order 1. Right? So this ratio can take values between 1 and 100, 1,000, 10,000. So the larger this ratio is, the more indicative of a two-layer circulation or gravitational exchange, let's call it, or estuarine circulation. The larger this ratio is. The smaller it is, it means that more unidirectional the flow will be in this system. Okay? So in the case of a river, this will be close to 1. Or in the case of a well-mixed system where you don't have return flow, wherever you don't have return flow or gravitational inflow, then this ratio will be order 1 or small, like you said. All right, so keep that in mind. Because so the larger this ratio, the stronger the gravitational circulation. So this ratio is typically greater than 1. That's what those glasses you can see there. Show me a weird Korean message. Doesn't want to show it again. So that's one parameter that we're going to consider, the circulation parameter. Okay, so the circulation parameter tells us how effective the system is in showing gravitational circulation. And then the stratification parameter, that's the second parameter. So remember, we're using this as surrogates of the other two that we looked at. The other two looked at diffusive versus advective effects. So now we're talking about the circulation parameter, which tells us how gravitational circulation exists, whether gravitational circulation exists in the system or not. So the next parameter is the stratification parameter. And this stratification parameter is the ratio of the top to bottom salinity difference, that is the stratification, divided by the mean salinity over the entire cross section. So expressed like that. So think about this and what range of values would you expect to see here? So again, let's think of a cross section. Let's just give some values, hypotheticals. Salinity at the surface, what do you like salinity at the surface to be? Any value. 0? And at the bottom? 35. So we have a difference of 35. What's the sectional average? Give me a sectional average. So throughout this cross section where we have 0 salinity at the surface and 35 at the bottom, in this very idealized estuary, what's the average cross section? 20. Now salinity, 20. Fine. So what's this ratio? The stratification parameter will be then greater than 1, right? 35 over 20, which is almost 1.5. So that tells us very strong stratification. What about if we have 25 at the surface and 26 at the bottom, or 25 at the surface, yeah, let's say that. 25 at the surface, 26 at the bottom, and a cross-section average of 25.5. So this ratio will be 1 over 25.5, so it will be rather small. So you can see that this stratification parameter can take very small values meaning maybe 0.1, 0.01, 0.01 when it's close to mix, or 0.001 when it's close to mix. And in large values, the largest values may be 1.5, as we see, or maybe, I don't think 2, but 1.5 maybe. 1.5 means very strongly stratified, and very small values means homogeneous. So we're going to use these two parameters to try to come up with a classification of S2A. So if we understand these two parameters, what they mean, then we're home free. So there you have, we've discussed this, that at mixed conditions, delta is equal 0. So when this stratification parameter is greater or equal to 1, then you have very strongly stratified conditions. Okay. So we have those two parameters now, and we can come back to compare advection versus diffusion to determine the diffusive fraction of the total upstream salt flux in an estuary. And we're going to call that diffusive fraction, we're going to call it nu. And they can be determined as a function of those two parameters, of the circulation parameter and the stratification parameter. So notice that we will define this diffusive fraction as the diffusive fraction of the total salt flux. So when this nu equals 1, it means that the total salt flux is caused by diffusive salt flux. It means that mixing is the one in charge of bringing salt into the estuary. It means that there's no gravitational convection or gravitational circulation bringing salinity into the system. The mean circulation is irrelevant in driving salt into the system. That's when nu equals 1. That is, mixing dominates over advection. And then when nu goes to 0, approaches 0, it means that this is very small with respect to the total salt flux. So when nu approaches 0, it means that the advective salt flux will be much more effective than the diffusive salt flux in distributing the salt in the estuary. And when you have that nu is between those two, you have that both advection and diffusion are important. So here's a trick, or the beauty of this approach is that with the stratification parameter and with the circulation parameter, we can determine how this diffusive salt flux behaves as a function of those two. Remember, this diffusive salt flux, if we go back a little bit, can be derived also from the Rayleigh number and the tidal mixing parameter that we defined. Right? So here's the classification, or rather the distribution of the diffusive salt flux. These are the lines of diffusive salt flux as a function of the, what is this parameter we said? It's the circulation parameter. U sub S is the surface flow, and U sub F is the cross-sectional average. And this is the stratification parameter. So stratification parameter and circulation parameter. Remember, a circulation parameter of 100 or 1000 means what? Means that gravitational circulation is very active in this system. If it's around this end, it means that the net flow is practically unidirectional. Now the stratification parameter, remember, these low values mean that the water column is mixed, and up here it means that it's highly stratified. So now remember, here's what we said about the diffusive salt flux. That when it equals 1, it means that there's no gravitational convection, that all the salt flux is produced by mixing, by diffusive effects. And this is when nu equals 1. It doesn't matter how stratified the system is. All the salt flux is produced by mixing. In the other extreme, you have here where the salt flux is produced by gravitational convection. And notice that it exists for values of the circulation parameter of around 3 maybe, 3 or greater. You have that the salt flux is produced by estuarine circulation. That's what this line represents. Notice that even at not very strong gravitational circulation, you have that the salt flux is dominated by the gravitational convection because the system is very strongly stratified. So think of a very strongly stratified system with strong tides, or that are not able to mix the water column, that keep it stratified. And so in such a way that the mean flow might not be as strongly as a gravitational circulation, but the salt flux is produced by convection, by the gravitational circulation. So this might be like a salt wedge type of estuary that's strongly stratified, the tides are strong, but the mean flow is not produced by mixing but by advection of salt. So that's what this line represents. In this case would be maybe fjords, right? In this case would be fjords, or here, where you have some stratification or strong stratification, and you have gravitational convection active. And all of the salt flux is carried out by gravitational circulation. So most systems will be here where you have both gravitational circulation and mixing. Most systems. In most places you'll have that they will fall in here. So do you understand this distribution? One thing that to note is that the advective component of the salt flux is not necessarily proportional to salinity stratification. So the advective component of the salt flux, which is this line, is not necessarily proportional. Notice that even at high stratifications, you'll get that the advective component of the salt flux can be small, even in these cases. In these cases, where you have that the salt flux is produced by mixing, but not by gravitational convection. Okay, so that these lines again represent the component of the salt flux due to diffusion. So we can now place several systems in this context of of the circulation parameter and the stratification parameter. And this is what the Hansen and Rattray classification of estuaries is like here. We have these different types of estuaries: 1A, 1B, 2A, 2B, 3B, 3A, 4. Now, some of you have the notes right in front of you, but if you try not to look at them, I'm going to ask you, given that you have this circulation parameter here and the stratification parameter, and what you've seen in the previous slide, we saw the diffusive flux, the fraction of the diffusive flux, drawn on this parameter space also. So given that you know what you know, what do you think? Let's say, how would you characterize these systems of type 3, given this circulation parameter and this stratification parameter? If you remember this, the diffusive cell flux was dominated by advective, by gravitational circulation. So this type 3 would be fjords. Yes, fjords. Salt wedge will be slightly different. But fjords, why do you say fjords? Because the gravitational circulation is strong, and so this would be strongly stratified and this would be weakly stratified. So in fact, you have different types of fjords here. This J sub F, not J sub F, JF represents Juan de Fuca Strait. This is close to the place where Amy was talking about yesterday in her seminar. If you weren't there, you missed it. So you don't know where Juan de Fuca is, right? Right? Where is it? Can you tell us where it is? That's between and the U.S. Yeah. So what's that island of Canada? Yeah, Vancouver Island. Yeah. So you know where Juan de Fuca is. So, and the broken line represents the range of circulation parameters and stratifications that particular system can attain. This is Silver Bay. That's another fjord in Alaska, and this is under high river discharge conditions and under low river discharge conditions. That's why it's under the stratified situation and the not so stratified situation. So these are deep systems where you have strong gravitational convection, highly stratified and low stratification. So that's the type 3 systems, highly stratified estuaries. How about the type 2? How would you characterize those type 2 estuaries? The salt wedge. Why salt wedge? Weaker stratification. Well, really, the salt wedge is number 4. So number 2 is most estuaries of temperate regions, partially stratified or partially mixed. You see, you have gravitational convection active, but the salt flux is carried out both by mixing and by gravitational circulation in this part. So actually, let me put it on top. So you see, you have a nu of 0.9 or 0.5. So in this whole region, the closer you get to this area, the more mixing there is. The more mixing of salt there is. The closer you get to this green diagonal, the more gravitational circulation is in charge of causing this transport of salt. So anyway, we have various examples. We have the Mersey, which is an estuary in the UK. So the UK estuaries mostly fall here because they tend to be weakly stratified, but you have some sort of gravitational convection also. So you have the weakly stratified. And then this is the James River, the J, at different locations. This is the 17 is closer to the mouth, and this is closer to the river, I think. But what you see here is that it's a partially mixed estuary with some stratification. So that 10 to the minus 1 in the stratification parameter is the one that divides some stratification from weakly stratification. So practically in the same area here in the James. Then this is the Columbia River. This is the Columbia River at low discharge conditions and at high discharge conditions. So why would the Columbia River, when it's high discharge, be here? In this part. This type 1 would be what?
The high discharge.
The type 1 would represent, remember, unidirectional mean flows. So almost like a river. So that's why the Columbia River estuary, under high river discharge conditions, so a lot of discharge, it's practically pushes the salinity out of the estuary, and you only have tidal pumping with every tidal cycle, and that's why it's here close to the salt wedge, but also unidirectional flow. So you only have salt coming in with every flood stage during high discharge, and the mean flow is practically out throughout the entire Columbia when you have high discharge conditions. Because you have a lot. What do I mean by a lot of freshwater discharge? So if I have any idea in terms of cubic meters per second when the Columbia is discharging strongly, it's almost like the Mississippi, 30,000 cubic meters per second or so. Does that mean anything to you? If you remember the Chesapeake Bay, the mean discharge to the Chesapeake Bay is 2,200. So 30,000 would be 15 times larger than the average discharge in the Chesapeake Bay. The St. Andrew Bay, the average discharge is around 40 cubic meters per second. 40. Here, for the Columbia, where it's large, we're talking about 30,000 cubic meters per second. So you can imagine how that flushes the salt away. And only during flood tides you get some salt coming in. So that's what causes the strongly stratified conditions here, but unidirectional flow through the section, through the cross section. So these are unidirectional estuaries that are mixed and stratified. And the number 4 is the salt wedge type of estuaries, and this is the Mississippi under high river discharge conditions and under low river discharge conditions. Notice again that under high river discharge conditions, the mean flow is almost unidirectional, and during low discharge conditions, it becomes more like a typical estuary, but it's still a salt wedge type of estuary. So again, you can, with these two parameters, you can place your estuary in this diagram, and you can learn about how the salt gets pushed into the estuary and how it dynamically how it behaves. That's why this classification is so useful. The drawback, well, we'll talk about the drawback in a minute. Let's review the types of estuaries. So the type 1 is that there's no vertical structure in the flow, as we discussed. So what that means is that there's seawall flow practically at all depths, and it's dominated by diffusive flux of salt. So for 1A is well mixed and 1B is stratified. Then number 2, there's a flow reversal with depth, and you have both the contribution of advective and diffusive fluxes of salt. And for 2A you have well mixed conditions. Many estuaries in the UK fall here, and then you have the stratified systems here. Then you have number 3, where you have strong gravitational circulation and where the advective flux of salt dominates. And number 4, we have the salt wedge type of estuary. Okay, you can use all these concepts in a very useful manner, but before we go there, let's discuss this a little bit. One of the drawbacks of this classification is that it's you have to prescribe this circulation parameter and this stratification parameter. So it's not that easy a priori to know these. So you have to know a lot about the system before you can. So by the time you know what these are, you know where the system is going to fall. So that's a drawback. So I mean, it'd be easier if you with a simple measurement of flow, of how strong the flow is and how strong the river discharge is, you can place the system in a classification. And I will talk about that at the end. When we're done with all these selected topics, I will bring that up again, because Geyer has come up with this new approach to classifying just on the basis of those two simple parameters: the flow, how strong the flow is, and how strong the river discharge is. So on the basis of those two, you can come up with a classification like this, and I'll come back to that later. So this is a drawback, again, because by the time you understand what this U sub S over U sub F, that is the circulation parameter, by the time you understand what it is, you know where it's going to fall in this diagram, where in the x-axis of the diagram. And by the time you know this other parameter, you also will know whether it's strongly stratified or well mixed. So you cannot predict whether it's going to be one way or the other. So, well, but that's okay. I mean, you're so picky. But also, what other drawbacks that you'll find from this approach? One is that it assumes lateral homogeneity. And we have discussed that our hot topic is that recently is that we're trying to decide, or people have proposed that the lateral shear in the flow, in particular the advective term that's related to the lateral shear in the flow, it might be important, order one contributor to the long estuary dynamics. That is, you don't have pressure gradient versus friction as the order one momentum balance. You must include also the advective terms. Apparently, that's where we are. So this approach does not include the advective term. What else? It doesn't take into account temporal variation. You could sort of do that, include temporal variations by doing this, but this would be seasonal variations. You don't know how it changes within the tidal cycle, for example. But in general, I think it has a lot of insights, both in the sense of that it tells you how the mean flow is, how the stratification is, and how the salt flux takes place in the system. So those three pieces of information about the system you can gain from placing a system in this diagram. All right, you can use also these concepts to estimate flushing time. You can use these parameters to estimate flushing time, and this was first used in 1991. What you can do is that if you calculate, going back to the previous lecture, if you use the freshwater volume as defined by the freshwater fraction times the volume of the system, and then the residence time equals that freshwater volume divided by the river discharge, then using this representation of V sub F, you get this. And then the flushing rate is the volume divided by this, which is volume divided by the residence time, which is the inverse of the salinity fraction times the river discharge. So you can calculate the flushing rate of a system with a lot of measurements of salinity throughout the different months, if you want. And you know the river discharge. You can calculate the freshwater fraction, so you can generate a plot of river discharge versus flushing rate. And you might find that they're aligned like that. The higher the river discharge, the more efficient the system is to flush, so the higher the flushing rate. So you might get the observations that given by those green dots. So then if you feed a line and bring it to the origin, then you can calculate the diffusive salt flux, the diffusive fraction of the salt flux, by dividing this intercept of the flushing rate, that is the flushing rate at zero river discharge, divided by the flushing rate at the time of your observation. So you can see that the greater the flushing rate, the lower this nu will be. So the lower the nu, what does it mean? Well, it says right there. The less the diffusive effects of the salt flux, and the more the advective effects. So again, with this relatively straightforward approach, and actually you could do it for St. Andrew Bay. If you talk to Pat, he has measurements of salinity profiles throughout the year. I think he's probably completed a full annual cycle now. So you can get the flushing, the freshwater fraction from salinity measurements, and you can get the river discharge at the time of measurement. So with that, you can calculate the flushing rate and generate this curve, bring it to the origin, and then calculate the diffusive fraction for the salt flux. And that'll tell you what process is responsible for bringing salt into the St. Andrews Bay. So these are neat ideas that are relatively simple and have not been used a lot. So this is just so that ideas that I think are very interesting, that for some reason have become fashionable. And here, because it requires an annual cycle of salinity, maybe to get enough points, or a representative plot of flushing versus river discharge, you need a lot of measurements. But when you have a lot of measurements, you probably do it. All right, so that's it for today.